So, in our previous video, we had talked about various types of operators. We had talked about arithmetic operators, relational, logical, ternary, unary. And if you want to know more about these operators, you can definitely watch the previous video. The link will be in the description. But in the previous video, we had not talked about bitwise operators, as I wanted to make a detailed video on that because bitwise operators is like another topic in its own. So rather than discussing there, because that was quite a long video, so I thought let's just make a separate video for that. So this video is going to be all about bitwise operators, and you'll be learning a whole lot of things. I mean, if you never stumble on this kind of operator, then you will be learning a lot new things in this video. Hey guys, my name is Rajat, and welcome to Bite the Code. So, what are bitwise operators? So, bitwise operators are used to perform manipulation on individual bits of a number. So, like we have few operators, bitwise operators that allow us to, you know, to operate on numbers, and we can do the bitwise manipulation. So, but before we take a look at the different bitwise operators, let us understand how to convert a decimal number to binary number and vice versa. Okay, so the decimal or the base 10 number system is used in everyday life, but the binary number system is the basis for representing data in computing systems. You will now see how to convert a decimal number to a binary number. So what could be the step one? Let's divide the decimal number by 2. Okay. Step 2 would be write the number on the right hand side. This will be either 1 or 0. Okay. Step 3, divide the result of the division, and again we have to divide it by 2 and then write the remainder as we have done in the previous step. Okay. And then we need to continue this process until the result of the division is 0. Okay, what will be the step 5? The first remainder that you received is the least significant bit, and the last remainder is the most significant bit. Okay, if it doesn't make sense, we are going to take an example and see how actually we convert a decimal number into a binary. So let us take this example here. Here we have decimal number as 25, and we are trying to get the binary representation of this number. Okay, let's see how can we do it. Let me go a bit down to get a nice empty area. So suppose I have this number. Let me draw it. So we have this number 25 and we need to divide it. Let's divide it by 2. So by dividing this 25 by 2, we'll be getting 12. But 2 multiplied by 12 will give us 24, not 25. So 1 is our remainder, right? Now let's divide 12 by 2 again. Okay, this time 12 is completely divisible by 2. So we get a remainder of 0. Let's divide 6 again. Okay, this time we get 3. So again, we get a remainder as 0. Now, when we divide 3 by 2, we'll be getting a remainder as 1, right? So now what about 1 here? When we divide 1 by 2, we'll be getting a remainder as 1 again. So if you see this, let me just zoom out a little bit. If you see this, I had told you whatever you will get at the first time, this would be the least significant bit, and whatever you will get at the very end, this will be the most significant bit. Okay, so whenever we got whenever we are finished by dividing our decimal number by 2, how we will represent this is by going from down to top. So we'll be writing the binary representation of decimal number 25 is 1, 1. We have two zeros and then a 1. Let me just go a bit down. Okay. So the binary representation of 25 is 1101. 11001. Yes, it is matching, right? So this is the binary number. I hope you are clear with this, how we will get a binary from a decimal, right? If you have any doubts, guys, you can always comment down. I'll definitely answer it. Okay, let's move on. So you will now see how to convert the binary number back to a decimal number. Now, suppose you have a binary. Now you want to, get the decimal representation of that binary number. So how that binary will be if we convert it back into the decimal number. So let's just see how can we do it. So the decimal number is equal to the sum of binary digits. We are representing it as d base n times their power of 2, which is 2 raised to power n. What I just said, I'll explain it with an example. Okay, so we already have this binary number, a binary representation of 25. So let's just take the similar example. Okay, let me just copy this. Mm, Let me go to our board. Okay, so here you can clearly see we have this box here. Now, in that, we have our binary representation of 25. So we have from the left hand side, I'm reading 11001. Great. Now, look at this first box on the right hand side. So we have inside the box, we have a binary digit. So either it would be 0 or it can be 1, right? So above this box, you can see there is this 2 raised to power 0 equals 1. This is the weight of this particular box here. Okay, so weight, I mean what? So this is the first box. We will always move from right to left. So right would be the first box, right hand side would be the first box of yours. So inside that we have 1, above that we have 2 raised to power 0, which is 1. So always consider from the right hand side. So first box would be the power of 2, right? So we are going from 0, then 1, then 2, then 3. So why we are taking only 2, 2 to the power 0? Because 2 means we are in binary system, right? We are converting from binary to decimal. So that's why 2 raised to power something. So for the first box, we have 2 raised to power 0, which we all know anything raised to power 0 is 1. So we have the weight of the first box as 1. Okay, let's move on to the second box. So in the second box, we have inside 0, and above that, we have the weight as 2. Why? Because this is the second box, and first box was 2 raised to power 0. So this has to be plus 1, 2 raised to power 0 plus 1, which is, of course, 1. So we have 2 raised to power 1, which is equals to 2. So the second box have the weight as 2. Let's move to the third box. Here, we have 2 raised to power 2, which has the weight as 4, as you can see. Fourth box, weight as 8, and then fifth box, weight as 16. And even whatever the binary number you have, you can go just 2 raised to power 5, 2 raised to power 6, and so on. Now, what we will do, you just have to consider only those boxes which are actually having 1 inside of it. Okay, let's again start from the right hand side. So here we have 1 here. So we'll consider the weight of this box. So what is the weight of this box? The weight is 1. So we are writing 1 here. Okay. Add a plus symbol. Now what about the second box? No, we don't need to consider this. Why? Because we have 0 inside. Okay, so we'll move further. So even if you write 0, that doesn't matter. Let's move on. Okay, again we got a 0. We will not consider. Let's move on. Okay, so this box, we have 1 here. we'll consider the weight. So here we have 8. Let's move on to the last box. We have 1 again, and the weight of this box is 16. Now what we will do to get the decimal representation of this binary, we will just add these numbers. Okay, so when you add 16 in 8 with 1, you'll get 25, which is actually true, right? As you can see, let me just zoom out. You know this, right? We have uh, got the binary number of 25 as this, and again we have verified that this is correct. So this is how you will you will convert from binary to a decimal number. I hope this is all clear. Okay, so let's move on to the next part. So as I have told you, we have few bitwise operators that allow us to operate on bits. So as I have told you, this bit manipulation, this is just an introductory video to bit manipulation, like how we, you know, operate on bits. But bit manipulation is like a very vast topic in its own. So if we have to discuss it uh, in much detail, this is really not possible, guys, in this video. So we will definitely discuss it, but I'll make a separate video for that. And in that, we will be discussing all about bitwise manipulation, and we will go a bit deeper inside the bitwise concept. So let's just now keep be on the surface and just get an introduction of each and every operator that we have in this. So first is bitwise OR, that as you can see, we can represent it with a single, what do you say, a pipeline symbol. Okay. So what it will do, it will it returns bit by bit OR of the input values. So if either of the bits is 1, this is important. Just listen to me very carefully. If either of the bits is 1, then it gives 1, else it gives 0. So it will always look for a 1. And even if it got, a single 1, it will say, oh yes, I found a 1. Else it will just say, okay, there is no 1. Okay, let's take an example now. So suppose we have 10 and we have a decimal number 5. Now we want to operate on these by using this bitwise OR. So what this OR will do to 10 and 5? Let's see here. So suppose we have a variable with the value 10, and in binary you can calculate how to convert this 10 into binary. You know this. Now you will get 1010, which is 10. Now you have a variable b, you have 5 in it, and you can convert it also. You will get 0101 in binary. Okay. Now when you do OR operation on these two binary numbers, so as you know, OR will look, it will start from the right hand side. Okay. So it will look at this first bit of 10, which is in binary is 1010. So it will take this, see this 0. Okay. It understands, okay, this is 0. Now it will have a look on this last bit of this digit, which is 5. So this is 1 here. So as we know, OR will, what it will look for, 1. If it is not 1 here, it will look here. Okay, yeah, I got 1. So it will just do what? It will result it in 1. So we have this 1 here because we have either of the bits of these two numbers, we have 1 here. So that's why the resultant is 1. Okay. Now let's move on to the next bit of this 10 digit here. So we have 1 here, and on this 5 we have 0. So okay, but either of the bits is 1, so the output will be 1. Again, move on to the next bits of the two numbers. We'll get here 0. Okay, let's see here. Okay, yeah, we got 1. So either of the two bits is 1, that's why we got 1. Again, either of the two bits is 1, that's why we got 1. So when you convert this result here, you will get a decimal number of 15. This is how OR operator works on bits. Let's see AND operators now. So it returns bit by bit AND of the input values. So if both the bits are 1, then only it will give us 1, else it will give us 0. This is pretty straightforward. Both the bits has to be 1, then only you will get 1. Otherwise you are going to get a 0. Let's take the same examples again. A as 10, B as 5. Convert both the decimal numbers into their respected binary numbers. Now when you do bitwise AND, you will see that okay, either of the two bits, like both the bits are not 1, only one bit is 1. That's why you will be getting a 0, because in bitwise AND you need to have both the bits, like in this example you need to have both the bits as 1, then only you will get 1. Otherwise you are going to get a 0. So okay, that's why a 0 here. Again, no two ones, that's why 0. Again 0 and again 0. So the result will be 0, right? Okay, great. Let's move on to the next operator that we have. Okay, this is a left shift operator. So it takes two operands and left shifts the bits of the first operand. The second operand decides the number of places to shift. So it will zero on voids left as a result. So, okay, I think this definition is not making any sense much, but when we will be seeing an example, you will be understanding it better. So let's take an example where we are left shifting 10 to one place. Okay, let's see what does it mean actually and why the output is 20 here. Okay, so let me go to my board and I hope this is okay. So our number is 10. Okay, and the binary number for 10 is 1010, right? Okay, so the statement is something like this. So 10 left shift 1. So this operand here is what this left shift operator will operate upon. And this operand here will tell this left shift operator how many places, how many bits you need to operate on. Okay, what does it mean? Okay, I think it's not making any sense. Let me just, okay. So here, when we say 1010, let me just represent this 1010 in 8 bits of computer memory. So let me just say this is 1, 2, 3, 4. We say 5, 6, 7, and this is 8. So we have this 10 and we are representing it in a system which is having 8 bits in it. So when we have a number having 8 bits, so you have to fill all the remaining places with the 0. So why 0? Because this is a positive number, positive 10, right? So we are not going into this positive negative notation and binary, but we will talk about it later in some other video. Okay. So, okay, we have the number. Now, what does it mean when we say left shift this 10 with 1? So, what actually we mean is left shift this 10. So, right now, this binary is making the digit in decimal as 10, right? So, when we say left shift every bit of this 10 to 1, so that means just left shift each bit forward. So we will move this 1 to this place, okay, to this place, then we will move this 0 to this place, then 1 to this place, and then 0 to this place. So that means when we left shift this 1010 to one place ahead, we'll be getting 1 0 1 0. But you can see this is a void, so we will fill this void with 0, and these are also void, so we will fill these voids as well. So now we have our 10, which is not actually a 10 now, but we can see we have our 10 here, which is which has been left shifted to 1 as we wanted to. Now, when we convert this number here back to the decimal representation, you know how to convert back to the decimal from binary. So when you convert this number back, you are actually converting. Okay, we'll see. This is having a power as, sorry, I need to write the weight. So this is 2 raised to power 0 with a weight as 1. This is 2 raised to power 1 with a weight as 2. This is 2 raised to power 0, 1, 2. So it will be 4. This will be 2 raised to power 0, 1, 2, 3. This will be 8. And this will be 1, 2, 4, 8, 16. Right? So now we will consider only this weight because it is having 1, and only this weight which is having 4. So when you add these two places, you will say 16 plus 4, which is actually equals to 20, right? So 16 plus 4 is 20. So actually now this 1010 is not actually a 10. This is actually becomes 20. So this is how you left shift numbers, and this is how left shift operators work. I hope this is clear. Okay, let's move on to the signed right shift operator. Okay, so what about right shift operators? So here we are saying signed right shift operators. So what do we mean by this signed thing? So let's talk about this first. Signed means when we are representing a decimal number in binary, we are considering the sign of that number as well. So basically, we mean whether the number is positive or negative. So when we had talked about left shift operator, we are not saying signed or unsigned, but actually there is no such thing here in Java. So okay, so by when we are saying the right shift operator, then we have to consider whether it is signed or it is unsigned. So what does it mean? So when we say signed, then we means uh, we care about the sign also. So this, can you see this most significant bit? This most significant bit we'll be using to representing the sign of that number. So okay, this is all about signed. And what about this right shift operator? What it will do? It will do the pretty much same thing as left shift operator has done, but instead of left shifting the bits to the left, it will right shift, bits to the right. Okay, so that's the whole difference. So it takes two operands and right shifts the bits of the first operand, and the second operand decides the number of places to shift. So it will fill zeros and voids left as a result, and if the first operand is positive, uh, it will fill 0, and else it will fill 1. So yes, it will fill either 0 when the first, if the operand is positive, and else it will fill 1. So why for positive 0 and 1? This is because of this signed right shift operator. So right shift operator considers the sign, and this most significant bit is used in that. So I'm not going into much details because this video can probably become so long if uh, here talk about the how to calculate, how to represent negative numbers in binary. So I actually cannot, explain you right here, but I'll give you a brief overview of it. So let's consider this simple example. Here we are taking an example of a positive number. So we know how to represent a decimal number into binary. So we have a positive 10. We have to say positive 10 because this is right shift operator. So this is a positive number. So we will represent it. Okay, guys, in my previous example, when I was explaining you about left shift operator, I had considered only 8 bits of a number because there I have considered that I am representing this number in a 8-bit system. But now, as you can see, I am considering it as a 32-bit number. So that's why I have these 8 bits here, like at this place, and at this place as well. So this is like 8 bits plus 8 bits, which is 16, plus 8 bits, which is 24, and plus 8 bits, which is 32. I hope my calculation is correct. Yeah. So, okay. But for the sake of simplicity, we'll be considering only 8 bits system. So in that system, we will be representing a number having only 8 bits. So let's just consider only this thing. So when we are converting this decimal number 10 in a 8-bit system, so we'll be getting some binary number as 1010 like this. Okay. So after right shifting it by 1, what we have to do is we need to shift each bit to right side. So we'll be shifting by 1. So what we will do, we'll shift this 0 to right. Okay, to right, there is nothing. So it will just jump from this cliff. Okay. So it just vanished. Now what about this one? Okay, so one will be shifted to this place. Okay, let me just not explain it to you like this. Let me go to my board. That would be super convenient to understand. Let me move a bit down. Okay, this place is perfect. Let me open my tab as well. Okay, so here we have a number. So we'll say 0, 0, 0, 0, and then 0 again, 1, 0, 1, 0. Pardon my handwriting. This is very weird one. Okay, so now this is our number 10. So we have to right shift it by 1. So what we will do, we will right shift it 1. Okay, we can't go here because I have nothing at this side. So what I have to do is I need to write something. Okay, so this place will be empty. Now I have to shift this one to this place, 0 to this place, and 1 here. So finally, I'll be having a number as 1. This will be shifted to this place. Now 1 is here. Now at this 1, we need to write 0. At this 0, we need to write 1. And what else? Remaining, these will get filled by zeros, as I have mentioned. So this is nothing but signed right shift operator. You will say it is similar as left shift operator. Yes, of course, because the number here is a positive number. So guys, always remember, whenever you have to see whether this binary number, how can we say this binary number is a decimal representation of a positive number? So you have to see this most significant bit. If you are seeing a 0 here, the binary number is a positive, a representation of a positive decimal number. And if this is 1, then this binary number would be negative. So you have to consider this. So what about this 101 now? What this number had become, this 10 has become, after right shifting it to 1, this has become 5. Why? Because you know 2 raised to power 0 is 1. So let me just remove this. Okay. So you know 2 raised to power 0 is 1. Okay. This probably will be 0. And then we have to consider 0, 1, and 2. And 4 plus 1, which is equals to 5. So when you right shift 10 by 1, you will be getting output as 5. Cool. Now, what about the negative numbers? So as I have told you, see, this decimal number is not simple now. We have a negative sign involved. So when converting this 10 to binary, how you will convert? I'll give you a overview. You will first convert it as you will convert a normal number. So suppose this, just ignore this negative for now, negative symbol for now. Now just convert this 10 to binary alone. So you'll get, what you will get? You will get 1010, right? So let me go to my board again. Let me go here. Okay. Yeah. So suppose first you will convert, a normal number to binary. So you'll get 1010. Great. Now, second step would be you have to flip each and every bit of this number that you have right now. So what I mean flipping is 1 will become 0 and zeros will become 1. So when you flip the bits, you'll get something like this. This you will say we have one's complement. Pardon my extraordinary writing. So this is one's complement. Okay, let me just zoom out so that you can see. Okay, so this is one's complement. Now what you will do after that? In third step, you will how you will get a negative number? You have to add 1 to this one's complement. Like you literally add. So how you will do this? I'm not explaining it to you, but I'm just doing it for you so that you can see. I'll explain it in some other video when we'll be discussing, in more details about all these things. So like right now, just bear with me and see what is happening. So when we do 1 plus 1, what we will get? 1 plus 1, you will get 10. So you'll get 0 here. 1 will be carry forward. You'll be getting 1 plus 0. This will be 1, and then you will get 1 again, you will get 0, right? So this is the negative representation of 10 in binary. Okay, now you will argue that okay, you said most significant bit will be representing as 1 if it is a negative number, but here we have 0. But my friend, I have not mentioned the other bits that you have in 8-bit system. So if you represent this number in a 8-bit system, you will get the most significant bit as 1 here. Okay. And actually you will not get 0 here. You'll get 1. Okay. Sorry. You'll get 0 here. Yeah. Like that. Okay. So this is something like this. So this is how you convert a simple represent a negative number here in binary. So let's just go back. So when you uh, convert this, get the binary representation of this number, you'll be getting something like this, as I have mentioned. So this is something like this, right? See, 1111 and 110. Let me just write it properly. 1 1 1 1, sorry, 0 1 1 and 0. This is the negative representation of the minus 10 in binary. Okay, yeah, this one. So, okay, we got this. Now what we will do, when you right shift this negative number by 1, what you will be getting? You will right shift as we have done here. You will again do the same thing. 0 will be shifted here, 1 will be shifted in this place, 1 will be here, 0 will be here. So you'll be getting something like this, which when you convert back to the decimal number, you will be getting minus 5. And this is what is signed right shift operator. This is all about it. Okay. And now we have another operator which is unsigned right shift operator. And that's why I told you signed is when we are considering the signs. And here we are saying unsigned, which means we are not considering the signs. So how in Java we represent this unsigned right shift operator? We do it with uh, three greater than symbols, right? So you will be writing three greater than symbols. So whenever you see this, you should interpret it as unsigned right shift operator. So working is similar to the signed right shift operator, but where it is different, we will see it with an example. So same example again, when you unsigned right shift this 10 by 1, you will be getting 5 as you are getting here, right? But where then what is the difference? Difference is in the negative numbers. Like here, as you can see, here we are also having this negative, negative sign when we are in the signed right shift operator. Okay, we in the output after shifting towards the right, we'll be getting a signed, uh, decimal number as output. But in unsigned, you will see when you right shift a negative decimal number, you will actually get a positive number. See, you are not getting any signs here, and this number is, see, what is the difference? When you were right shifting a -10 in signed right shift operator, you will be getting, you will be getting -5. And here you are getting some this value. And why is that? That is because we are not considering minus sign here. This is unsigned. So what it will do, it will not consider negative numbers, but it will just give you a positive number. So it will probably doing something like this. So when it is considering converting back to a decimal number, it is just taking the powers of all of these ones which are here. So as you can see, 2 raised to power 1 will be 1 plus 2 plus 4, plus 8 plus 16 plus 32 plus 64 plus 128 plus so on to it will go till here. And when you add all these powers of 2, you will be getting a number as this. You are not getting a negative number as output because this is unsigned. We cannot have negative or positive. We will always have a positive number here. Okay. I know the explanation was not quite satisfying, but because of this time constraint, I am not going in very depth. But as I have told you, we will be discussing it in some other video definitely. So that was all about bitwise operators. Let's move on to the next topic. Okay, so we have a tryout here. So we have this code here. Let me zoom a little bit in. So I think it is, uh, let me just go down. Okay, so this is a code, as you can see. We have just declared two variables, A and B, having the values at 10, 20. And here, what we are doing, we are left shifting this A, whatever the value is inside A, we are left shifting it by 2. Okay. And here we are right shifting the value of B as 3. Then we are doing something. See, we have this, we are using unsigned right shift operator as well. So again, we are right shifting A by 2. Then we are doing unsigned right shift on A by 2. So then we have another variable declared here. And now what we are doing, we are again right shifting C by 2, then unsigned right shifting 2, so that you can understand this right shift is signed right shift and this right shift is unsigned right shift. Okay. And here we are computing this. Uh, okay, so see, here we are doing something weird. We are left shifting, and that also we are doing unsigned left shifting. So have we read about this unsigned left shift? Yeah, definitely not, because there is no such thing in Java. You can't do this. There is no provision for this. Okay. And what about the other? What we are doing here? We are logical. Okay, we are now explaining here what is logical OR and what is the difference between bitwise OR. So we will see that also. This is bitwise OR, and here we are doing bitwise AND. You can, I'll provide this code in the description box. You can also copy it and run it on your system. These lines are just comments, so you can understand it, right? So I'll provide you this code in the description, and you can understand this code by running it on your system. So I'll execute it for you, and let's see what is the output that we are getting here. So see, we have got an output also. So you can just copy this code and run it in your system and observe how you are getting these outputs. Okay, let's move ahead, and next topic would be operator precedence. So, okay, let me just zoom out a bit. So, what is operator precedence? So, operators also have precedence. So, the below table lists the operators according to the precedence from highest to lowest. So, operators with higher precedence are evaluated before the operators with lower precedence. So, when an expression has two operators, with the same precedence, one after the other, the expression is evaluated according to their associativity. So this thing is important, that so what about when some operators have same precedence? Then we will evaluate them when in the order of their associativity. So associativity comes in when we have same precedence of some operators. So the associativity of operators can be left to right, or right to left, or no associativity at all. So what do we mean by this? Let's have an example. We are saying, for example, num1 is equals num2 is equals num3, which in turn equals to 39. So internally, when compiler sees this, line of code, what it will interpret this line as something like this. So when it sees number 3, it will just put some parentheses around these number 3 equals 39. So first this 39 will gets, uh, assigned to this number 3, num3 variable. So when this got assigned to this, then it had successfully solved these parentheses. Then it will just move on to this num2. Again, we have a parenthesis here for num2. Then we have to solve this. So num2 is equals num3, and num3 is having a value as 39. So num2 will also have a value as 39. And then finally, we have this num1. So num1 will also have a value as 39. So because why we have to evaluate this inner parenthesis first? Because parentheses have the uh, you know precedence, most precedence out of all these operators here, as you can see. So first always parentheses will get solved, and because here are three parentheses, so which one we have to solve? So we are here going from right to left. See, first this one gets solved, then this one gets solved, and then this outer parenthesis got solved. This is the right associativity. So associativity of parenthesis is from right to left, right? Like that. So leaving all three variables with the value of 39 as we have seen. So see, equals operator has right to left associativity. On the other hand, when we say 84 divided by 4 divided by 3 is treated as like this. See, this is all depends on this equals to operator. Precedence of this also matters, and this operator also matters. So equals, see the precedence of equals. So equals assignment operator is here, see here, and its associativity is right to left. Okay, so that's why we are moving from right to left. Okay, now what about this division? So we know when we have such kind of arithmetic expression, what we will do something like this. So internally it will be represented like this. And now when we are talking about the division have to be done like this, right? We have to do division like this. So left to right. So first this thing got solved. We get some answer here. Then we have to divide that particular answer with 3. And then we got the whole answer. So the associativity of this division operator would be left to right. And what about this no associativity? So, like for example, postfix and prefix operators, these are those operators which do not have any associativity. So if you say something like this, num plus plus and minus minus, you are going to get an error. You can't do this. This is invalid. So let's just take an example here. So what about this expression here? How do you think this is going to get solved? So here comes the operator precedence in play. So first, what you have to do is see the parentheses. Where are the parentheses? So here are the parentheses. No matter what operation is having on these operands, you have to perform it first, because this is having the most precedence uh, uh, than any other operator in the Java language. So parentheses will get resolved first. So 3 plus 1 will be 4, right? So this is going to get this is going to get the second statement that we get. So 5 plus 4 multiplied by 9. So according to the BODMAS rule, okay, you will be, or if there is some other rule, so most probably multiplication would be the one that you have to perform first. So multiplication will have the higher precedence than this modulus or subtraction or positive addition symbol. So you have to do multiplication first. You will do 9 multiplied by 4. You will be getting 36. Then you have to perform this because modulus precedence is greater than positive and negative. Sorry, addition and subtraction operator. So you will be performing this. You will be getting a 0. Then what you have to do, you have to divide this 0 by 6 because division is having higher precedence, right? So you'll be dividing 0 by 6, then you will be performing at the end plus and minus. You can do either of them first, doesn't matter. So you'll be getting at the end as 4. So this is how you are going to solve. This is how compiler is going to solve your expressions. Okay, so finally we have a quiz time. So what I will be showing you now, you will be seeing three questions and you have to tell me the answers in the comment box. I'll be showing you the questions now. Just see this question and you can pause this video. You can analyze this little code here, okay? And you will be telling me in the comments that what will be the answer for this output. So just tell me what will be the output of this code. Pause the video now. Okay, so this is the second question. You can pause the video, have a look on it, and tell me what will be the answer for this output here. Time to move on to the last question of this quiz. This is the last question. You can tell me the answers in the comments. I'll also post a poll for this quiz in my YouTube community. You can also uh, try that poll as well. So this is it for this video, guys. I hope you have understood a lot of things about bitwise operators, how they work in Java, what different kinds of operators we have in Java. And if you have any doubts or any problems you are facing, you can definitely reach out to me. I have a Telegram channel as well. You can reach out to me there. You can post your comments, your doubts in the comment section down below. And I'll meet you in the next video, guys. Thank you so much for being here in this video. And take care and keep practicing. So, bye bye, take care, and be safe, keep safe. All the very best to your future. Thank you so much. Jai Hind.